Today we're going to explore another concept of calculus called the integral. So 1.3 is one type of integral of a function. Your essential question, how do you estimate on a graph the definite integral of a function between two x values, let's just say a and b, by counting squares? Probably the most challenging thing today is not the counting squares, but understanding the units of each of those squares. I'm going to use this example to kind of introduce the concept. So we've got a person that can jog a mile in 16 minutes. So this person goes 1 mile in 16 minutes. Okay, we're going to sketch a graph of a constant velocity function. That means that this person's speed doesn't change. Their velocity is always, basically, in 16 minutes they've jogged a mile. Okay, let's talk about what their velocity is then. So if we want to talk about units here, they're jogging 1 mile every 16 minutes. Or if we wanted that in miles per minute, then this would be the same thing as 1/16 of a mile per minute. Okay, so this is their velocity, and their velocity is in miles per minute. Okay, and their velocity, this is going to be their velocity graph. So I think I'll use velocity. We'll let that be v, which is going to be in miles per minute. Okay, and so then what's our x-axis or our horizontal axis going to be? Well, that's going to be our time, and that's going to be in minutes. So how about we let velocity be a function of time, so v of t. Okay, so the variables to be used will be v of t, and we should use for time, which is going to be minutes. How about we just use t for time? That doesn't look that good. Let's just use t, so it doesn't look like we're putting that into minutes. And time is going to be in minutes. Okay, because that's what it says. All right, so we figured out what variables we need to use. Did that. Okay, we can label our axes now. Okay, so our vertical axis is going to be the velocity, which is going to be v of t, or in other words, it's going to be miles per minute. Those are the actual units. And then our horizontal axis, we said we would label that with t, but that's actually going to be in minutes. So now we're going to find a shape on the graph that represents the distance traveled in 32 minutes. Okay, 32 minutes. Let's talk about that. So along my time axis here, since everything's happening in 16-minute intervals, I'm going to go ahead and do 16-minute intervals here. So 16 minutes, then 32 minutes, then 48 minutes, and so on. Okay. And now since our vertical axis needs to be velocity, that's going to be miles per minute. Okay. So let's just say they're doing the constant 1/16 of a mile per minute. Okay, so this isn't the best graph, but I'm going to go ahead and put that right here. So we're doing 1/16 miles per minute. Oops, sorry, miles per minute. Now I need a shape on this graph that represents distance traveled. I need to come up with distance traveled. Now you might be able to answer this question just in your head. How far has the person gone in 32 minutes? Well, if in 16 minutes they've gone 1 mile, how far have they gone in 32 minutes? Well, just double it, right? 2 miles. Okay, but that's great. We can answer that now, but we need to figure out a shape on the graph that represents the distance traveled in 32 minutes. So if I've got one axis that is miles per minute, let me write that here. And I've got another axis that is minutes. what do I need to do with these 2 units to end up with just miles? This takes you back to all the unit analysis that we've done, right? Basically, I'm going to multiply these, and the minutes are going to reduce. And that's just going to leave me with miles. Okay, so let's look at the shape that we could create here. Let's start with one of these squares, right? Because basically, multiplying the vertical unit by the horizontal unit is what we've done here. So I've multiplied base times height. So let's just look at one of these squares. The base is always going to be 16 minutes, because that's how many intervals, right? I've gone 16 minutes for every single interval. And then the height is always going to be 1/16 of a mile per minute. So just for one of these squares, if I find the area of one of these squares, I've got 1/16 of a mile per minute times 16 minutes. I'll put that over 1. So look what happens here. The minutes reduce, so I'm just going to be left with miles as my units. And so did the 16th. So I'm just left with 1 mile. So 1 square in this graph represents 1 mile. So what do I need to do to come up with 2 miles? Well, basically, that's 32 minutes, right? So if I go 32 minutes and I make this rectangle here, using the same exact velocity, 1/16 of a mile per minute, I'm going to go ahead and highlight this. And then I'm going to draw it down here. So I've got this beautiful rectangle that I'm making. Pretend like it's perfect. I know that doesn't look like a rectangle. Okay, along the base, I've got 32 minutes. My height's exactly the same because it's a constant velocity function. So it's 1/16 of a mile per minute. Let's do the math on that. So 1/16 of a mile per minute. I'm not writing this as a complex fraction like I did here, but basically this would be, dividing by 1 minute, which is the same as multiplying by 1 over 1 minute, right? So the minutes actually end up in the denominator. Okay, and then I'm going to multiply that by those 32 minutes. Yeah, and put that over 1. So the minutes reduce. This time 16 goes into 32, 2 times. So I'm left with 2 miles. Which, yes, we did not need to use calculus to figure that out, but we basically are using calculus. Okay? We're going from a rate of change, which is velocity, and we're going back to just displacement. Okay, so I'll talk way more about that. Let's see if I answered everything. Find a shape on the graph that represents the distance traveled in 32 minutes. Yep, it was a rectangle, right? I highlighted that. Okay, and then how far has the person gone in 32 minutes? 2 miles. And yes, you can do that in your head, but this is using integrals. So integrals is really like area under a curve or area under a function. Okay, I actually didn't graph the entire function. So the constant velocity function would have just been this like straight line. Okay, now I think I've done everything. So let's move on. So let's do an exploration on the back page. So very similar to what we just did. As you drive on the highway, you accelerate to 100 feet per second to pass a truck. After you have passed, you slow down to a more moderate 60 feet per second. The diagram shows the graph of your velocity, v of t, as a function of the number of seconds t since you started slowing down. So this is your velocity here. Oh, it's already written for us, v of t there. And this is in feet per second. Okay, and then our horizontal axis is time, and that's really seconds. They didn't write that for us. What does your velocity seem to be between t equals 30 and t equals 50 seconds. So between here and here, our velocity seems to be about 60 feet per second, right? So this is 60. All right, and then how far do you travel in the time interval? Okay, so right now, if I just look at this number here, if I just look at any of my outputs, I'm getting feet per second. If I just want to go back to feet, if I just want to know how far I traveled in this time interval, okay, I need to look at the area under the curve, right? So from 30 to 50, I need to think about this area right here. Okay, so let's see here. I was going 60 feet per second. Actually, why don't I write it, instead of just writing it like that, I'll write it like a fraction so I can work with the units. So 60 feet per second. Okay, and then I'm going to multiply it by how many seconds we're talking about, right? So basically I'm doing 60, which is my height, 60 feet per second. My base is going to be 20 seconds. And by doing that, what happens is the seconds completely reduce, and I'm just left with feet. I'm left with distance, how far I traveled. So what is that, 1,200 feet? That's integral right there. It's not always going to be that easy, but that's integral. Okay, explain why the answer to problem 1 can be represented as the area of a rectangular region of the graph. Shade this region. Oh, look, I already shaded it. We'll shade it a little bit better. How about that? So we can say that it's the area of a rectangular region because the area is equal to base times height. And if I look at that in units, right, looking at that in units, it's feet per, the base is going to be seconds, times the height, which is going to be feet per second. Those all reduced, just giving me feet. So that's why that's able to happen. Well, that's why that must happen. Okay, the distance you travel between time being 0 and 20 can also be represented as the area of a region bounded by the curved graph. Count the number of squares in this region. Estimate the area of parts of squares to the nearest 10th square space. For instance, how would you count this partial square? Uh-oh. I think I deleted that. Okay, no worries. Let's just count it. Let's make it look something like, how about like this? Okay, so this is what happens when I copy things. So just the shaded region, let's pretend like this is a square. Okay, and if I just wanted to estimate this partial piece, what would we say? Well, it's definitely more than a half, right? So maybe it's like 0.7, 0.6. Okay, so 0.7. Now, again, in this graph here, one square, let's think about just one square. One square, so the height is feet per second, and the width, well, the width of one square is 5 seconds, right? Oh, and what's the height? 10, 20, 30, 40, 50, 60. The height is actually 10 feet per second. You gotta look at those units. Guarantee that you'll make mistakes on that. And the width is 5 seconds. So let's think about what that means. What's the value of one of these squares? Just one square under the curve. All right, well, it's going to be 10 feet per second times 5 seconds. So the seconds reduce, and you're just left with 50 feet. So one square equals 50 feet. That's the distance traveled when you count one square. Okay, so let's go back to this. So from 0 to 20, okay, we're going to actually estimate. We need to count the number of squares and then estimate the area or parts of areas of the squares. Okay, so We can do this kind of by breaking it up. So maybe here I could draw myself like a rectangle. So let's see, this is 1, 2, 3, 4, 5, 6 squares by 1, 2, 3, 4, 5, 6 squares. So right here, I've got not going the right way. So 20, my bad, sorry. So it's 6 squares, 1, 2, 3, 4, 5, 6, to 1, 2, 3, 4 squares. Just making all the mistakes so you guys can not make them. So altogether there are 24 squares from 0 to 20 seconds, which is what it asked me to do, not 0 to 30 seconds. Okay, so there's 24 squares right there. Now I'm going to have to do a little bit of estimating here. So maybe this would be one whole one. You know, and you're just estimating the best that you possibly can. Maybe I'll take like this almost full square and this partial square and count that as 2, right? Or count that as one full one, so I'd have 2. Okay, so I'm just going to count that. Okay, maybe I'll take like this one, and this is a little too big, but I'm going to go ahead and count that as 3. And then I'll kind of overestimate now. So this one and this one I think together I'll count as 1. So I'll be 4. 1, 2, 3, 4. I've already counted that. And maybe I'll count this one as like a half. So maybe I'll just say that that's a 0.5. 1, 2, 3, 4, 4.5. So I've got an additional 4.5 squares over here, approximately. So I'm looking at about 28.5 squares. And, you know, we're not all going to be exact, okay? But you don't want to be too far off. So, you know, anywhere from maybe 25 to 30, something like that. And I think that's all that answer. Estimate the area or parts of squares to the nearest tenth. Yep. Okay, so I answered that one. Now, how many feet does each small square on the graph represent? Well, I've already told you that, right? So we went back over here, and we already calculated that. It was 50 feet per square. How far, therefore, did you go in the time interval between 0 to 20? Well, if I did 50 feet per square, and I've got 28 squares, 28 and a half squares. Well, the squares reduce here, and I just multiply the 50 times the 28.5 and end up with how many feet I traveled. 1,425. Problems 3 and 4 involve finding the product of the x value and the y value for a function where y may vary with x. Such a product is called the definite integral of y with respect to x. Okay, so based on the units of t and v of t, explain why the definite integral of v of t with respect to t in problem 4 has feet for its units. Okay, so right back to this right here. We took feet per second and we multiplied it by second, leaving us with feet. Okay, so we took v of t and we multiplied it by t, or time. And the units there were, for v of t, it was feet per second. That's your velocity. We're going to multiply that by time, which is seconds. That's going to leave us with feet, because these seconds reduce. Okay, number 6. Oops. The graph shows the cross-sectional area y in inches squared of a football as a function of the distance x in inches from one of its ends. Okay, this is very confusing. So the y is the cross-sectional area. This is going to be in inches squared. This is cross-section area. Okay, and that is in inches from one of its ends. So I think what's happening here is we've got a football. Okay, that does not look like a football, but just pretend. And we're taking a cross-section of that football, and we're looking at the area of that cross-section. And that cross-section is so many inches in from its end. Okay? So when I'm in the middle of the football, right, I'm getting the most area of the cross-section. All right. Estimate the definite integral of y with respect to x. Okay, so let's think about one square here. Just one square in here. Let's see. So along the x-axis, so the base of this square would be exactly 1 inch, right? So that's going by ones. The height, however, is going to be going by 5s, and it's inches squared. So 5 inches squared. So all together then, when I think of these, I'm going to take that 5 inches squared and multiply it by 1 inch, right? So that's going to end up giving me 5 inches cubed, right? Because it's inches times inches squared. So I get 5 inches cubed. So I'm ending up getting a volume. Okay, so I'm super confused. Estimate the definite integral of y with respect to x. Okay, so I think what's happening here is we are going to get the volume of a cross-section. So now it's going to be 3-dimensional. Okay, so I think that's what's happening. So now we're getting the volume of that cross-section. Okay, so we're going to estimate this. So let's do the best we can. So I'm going to try and make the biggest rectangle that I can here. You can do this a multitude of ways. I'll just go over here. Get a nice big one here. So that's going to give me 1, 2, 3, 4 by 1, 2, 3, 4, 5. So this is going to be 20 squares. Okay, so I'm just counting squares now. Let's see, I need more squares. So how about here I'll go, this is going to be 6 squares. And here approximately another 6 squares. Okay. I've got 2 more here. 2 more here. 1 here. 1 here. Yep, okay. So I think from there now I need to start estimating like how much of a square I have. So how about if I count these two as just 1? This is the hardest part, is like keeping track of all this. How about if I count this and this as 1? So I'll just put a little flash once I've counted it. How about I count, how about this one and this one can give me 1? Let's see what else I got here. How about, these are both about a half, so I'll just make this into 1. So we'll cross off that one and put a 1 there. These two, a little underestimate, but I'm going to go ahead and call those 1. I think this one and this one's probably a little bit more than 1. But let's go ahead and let's call that, I don't know, maybe 1.2 because I've been really underestimating. And this one, how about I call that a half? Okay, so let's see if I can now count. So I've got 20 here and 12. That's going to be 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44.2, about 44.2. Let's see if I got that last time I did this. I got 44. I think 44.2 works. All right, so see, every time I do these, I get it totally different. So I got 44.2 squares. I mean, not totally different. They're about the same. And each one of my squares is worth 5 inches cubed, right? So 5 inches cubed per square. Okay, so the squares reduce. 44.2 times 5 gives me 221. Wow, that worked out really nicely. 221 inches cubed. What are the units of the definite integral in problem 6? Inches cubed. What, therefore, do you suppose the definite integral represents? The definite integral here must represent the volume of that much of the football. Okay, so I think that we've answered everything. Let me go ahead and circle that so it stands out. All right, let's go back to our notes here. We've got a little bit more I want to cover with you. Pretty simple, but let's first talk about definite integral. Let's get an actual definition for definite integral. Well, I should say not an actual, but like a kind of an estimate or our own like verbal definition of what a definite integral is. So it's going to be the area under a curve over a specified region. And just like it said in our notes, right? So it's basically finding the product of the x value and the y value for a function where y may vary with x, right? X is the input, y is the output. So I can draw a little picture of this. Maybe I'll draw some crazy little curve. Okay, I'm going to call this f of x my function. This will be x. Now, in between two values of x, between like a and b, that's where you get the definite integral. Like you can definitely get an approximation or an area under this curve. So basically what we do is we take this length, and to find this base, the length of the base here, we take b minus a. And then we multiply it by whatever the height of the function is, okay, along multiple parts here, right? And so obviously the smaller you make these shapes, the more accurate this is going to be. So if I could actually make rectangles or make squares in here, the more accurate this is going to be. But the height, no matter where I am, the height is always going to be whatever f of x is, right? So this point here, well, here, let's use this point. This point here is a f of x. F of x is varying, right? Because when we get to b, it's still b, and then the height is still f of x, right? So it's varying. Okay, so your area is always going to equal whatever that length of the base is, so that's b minus a, times whatever your height is, and the height's going to vary. It's going to be f of x, whatever f of x happens to be. So in other words, this is going to be base times height. Now there are times where you'll have positive area and you'll have negative area. So for example, if I gave you a curve that looked like this, some of this area, the part that's above that x-axis, that's all going to be positive. But the part that's below the x-axis, that's going to be negative. So you end up taking the difference between these two, okay? Whatever you're left with ends up being your area. And then one more thing I'd like to talk about is the relationship between derivatives and integrals. So if we have distance or displacement, and we differentiate that, we take the rate of change, you get velocity. But when you have velocity and you integrate it, you get back to displacement, which is pretty interesting. And that's what we did, for example, here, right? We had a velocity function. We found the definite integral, and by doing that, those minutes reduced, and we were just left with displacement again, miles. Super interesting. Now, if I take velocity and I differentiate that, right? I find the rate of change of velocity. I'm going to get acceleration. But when I integrate, when I go backwards, and I integrate, so I think of it as going backwards, right? I take acceleration and I go back by integrating it back to velocity. We're going to explore this a lot more, okay? And so I gave you another graphic. I just went online and I Googled pictures of this. So I just borrowed other people's. I basically stole them. Don't tell them. So if you have your position function and you take the derivative, you derive the position function, you get to velocity, right? The rate of change of position is velocity, right? So you had feet here, now you got feet per second, okay? So here, this is, if we call this feet, this is going to be feet per second. Well, now I go to acceleration, right? So I take the rate of change of velocity over time, and that's going to be feet per second squared. I'm just using feet and seconds. And then I included this because I thought it was fun. So then if you take the rate of change of acceleration, you end up with a function we've never even heard of, which in physics I think you'll hear about it. It's called the jerk function. So this would be feet per second squared per second, or feet, per second cubed. And there's more. I forget. It's like snap, crackle, pop or something. I don't know. You can look on the internet. It's basically like Rice Krispies. So then if you go, I think of integrating as like going backwards. So now you integrate and you go the other direction. So if you have the acceleration function and you multiply that by time, you're going to end up with the velocity function, right? You're going to have one less seconds in the denominator. Okay, and then if you have the velocity function and you multiply that by time, you're going to go back to the position function or the displacement function.